Okay, I'll record that. Okay, so we did tension member design last week. So I'm going to just do a quick recap on that, highlight some of the common problems that people had or mistakes that people made in their submission, and then do a little bit more advanced in tension member design. So that'll be the first class this morning, and then we'll move on to compression member design after that. So just as a recap, what we're doing is we're looking at, once we know what the forces are in the members, so for example, we do the truss analysis, we work out what the forces are in the members, then we can design the members to resist that tensile force in there. Okay, so we're carrying out a design according to Eurocode 3, part 1. And when we do the more advanced design this morning, we'll actually go into Eurocode 3, part 1, part 8 as well. Okay, because that's what we're going to design. Last week, we looked at designing members that were loaded symmetrically. This morning, we'll look at members that are loaded eccentrically, okay, which is a very common example. So on the tension member, the graph here is your load against deformation. So if we have a tension member down here, it's supports on one end, can't move on one end, so lateral can't move one end, but on the other end, we put a force in subscript T onto it. Then this is the load displacement curve that we will get. So as we said on Friday, the load at the very beginning, it's in the elastic region. In other words, it's a linear relationship between load and displacement. So if I double the load, so start at 0, if I move up to here, if I double the load, then I will double displacement. So if I have put 50 kilonewtons on this, and I give me 1 millimeter deflection, if I then put 100 kilonewtons on it, it will give me 2 millimeters of deflection, or 2 millimeters of elongation, should I say. Okay, so it's a linear relationship between load and displacement. That's up until yield. So the relationship between load and displacement are between stress and strain, because stress is just load divided by the cross-sectional area, and strain is just the change in length, which is this value here, divided by its original length. So the original length here being, say, L. So stress against strain is a similar shape plot as load against displacement, because the cross-sectional area is constant and the original length is constant. So therefore we get the same shape of curve. So when we're in the elastic region up until the yield point here, as I said, it's a linear relationship between load and displacement, or between stress and strain. And that relationship is described by Hooke's law. And Hooke's law tells us that it's the proportionality between stress and strain. So if I turn this into, if this was stress up here against strain down here, then we have the relationship between stress is equal to Young's modulus times strain. And then we know that stress is equal to the load in T divided by the cross-sectional area, all into Young's modulus, and we know that strain is equal to the change in length divided by the original length. So therefore we know that the force, tensile force, is equal to, sorry, that's a T down there. Tensile force is A E times sigma, or sorry, times delta divided by L. Okay, so the cross-sectional area times the Young's modulus divided by the change in length over the original length is equal to the force. So if I take that down here, the force is equal to A times E over L, all multiplied by the change in length. And this AE over L is the stiffness of the section. Okay, so that's the stiffness of the section. So when we have it up here, stress equals Young's modulus times strain. That's the material stiffness is Young's modulus, so it describes the linear relationship between stress against strain, and that works up to the yield point. And then we can also turn that into the equivalent of load against displacement. So in this graph here, we now have the slope here is actually AE over L. Okay, because we're plotting load against displacement, it's AE divided by L. Okay, so load is stiffness times displacement, and the stiffness value K is AE over L. So if we double the cross-section area, we double the stiffness. If we double the Young's modulus, so change the materials that we're going to use, we're going to double the load that's going to take for a given displacement. If we double the length, then what we're going to do is we're going to halve the load that's needed for a given displacement. Okay, so AE over L. And then in our design, so then we have the yield point that happens here. So this is where it doesn't become linear anymore between load against displacement, and that's described as NY and displacement delta Y. We have a plastic region here, so it's the NPL, so that's the plastic region, which is effectively after it yields. And then we get some strain hardening after that. So in other words, strain hardening means that as we still stretch it after a little bit more, we end up putting more force into it until we get to the ultimate force here in nu, and eventually it's going to rupture at the very end. So as a recap, what we said is that in a member, away from the connections we designed for the yield load, which is NPL RD, or NY, which is NPL RD times the cross-section area times the material yield strength divided by the material factor safety gamma M0. And then at the connection, say if we have holes in there at the connection, we're allowed to have some more brittle failure, we're allowed to push a little bit harder there. So therefore the ultimate strength, so we're going to go to this part of the curve up here, the ultimate strength is the net cross-section area down here, times the ultimate strength. We're going to multiply by 0.9 to reduce it down because of the uncertainty associated with the ultimate up here, and divide that by gamma M2, and gamma M2 is 1.25 because of the non-ductile nature of the type of failure in there. Okay, and then we always check the utilization ratio being the demand, which is the load that we put on the section here in T, divided by the resistance, and that has to be less than 1. In other words, that the demand has to be less than or equal to the capacity of the section. Okay, so that's what it translates to into the code, as I said. So NTRD in there, so the resistance of the member to the tensile axial load is the minimum of the plastic resistance away from the connection, which is AFY times gamma M0, Fy being the material strength. So for S275 steel, for a thickness of less than 40 millimeters, that's 275 newtons per millimeter squared, A being the cross-section area and gamma being at 1.0. And then the ultimate strength is 0.9, A net, Fy, gamma M2 in there, and I described that already. Okay, so here's the first general mistake that lots of people, or a number of people, made. So people would have calculated in the first assignment that you did, people calculated the plastic resistance using this formula here, and calculated the ultimate resistance at the two cross sections. So the cross section basically straight down, which is one hole, and the cross section where you go staggered because of two holes, because it's the staggered bolts in there. So that was fine. So that was the 3 checks that were done. But then you need to make sure you put the line at the very end that the minimum, the tensile resistance is the minimum of all 3, and actually write the number at the very end. So at the bottom of my page, I should see NTRD equals and then the value at the bottom. So and that should be a square box around it or something. So it's very easy for me to see if I'm the designer, or if I'm going to detail it, or I want to try and check that. I look at the number at the very bottom. That's very clear what is the answer. I shouldn't have to go back up 10 lines to find out what is the answer. So you need to put down that the tensile resistance is the minimum of all those 3 calculations you did, and equals the number, whatever they ended up as. And then at the very bottom, then you say NTRD equals, and write out what the number is. Okay, so that was the first thing, that there was a number of people hadn't done that. The second thing is one that I'm more concerned about. The second one was the factors of safety here that were used. What people were using the wrong factor of safety, and the third one was that people used the wrong yield strength and ultimate strength in there. Okay, so when we go to ISEN 1993 Part 1, 6.2.3, I asked you to make sure you downloaded that from the NSAI website. We're following this, where we basically want to have the demand divided by the capacity less than 1. Now, some people wrote this equation down at the very end of their calculations, but I did not give you a demand. You only had to work out the capacity, so you weren't able to use this equation. So just be careful. Don't mix up the demand and the capacity. So we're working out the capacity of the section. That's how much load we could put on it before we get yield or get damage at the connections. And the demand then is what we work out from our structural analysis. If we do, say, get a truss and resolve out the force of the truss member, that's the demand that we get. So we didn't have that in this example. So then we use these two equations. So the first thing is, when we go to the national annex at the back of Eurocode 3, Part 1, the Irish version, ISEN, and go back to the national annex at the very end of it, we can see that the material for buildings to partial factor safety is gamma M0 is 1, gamma M1 is 1, and gamma M2 is 1.25. So a number of people put gamma M0 is equal to 1.1. Okay, so other countries do have gamma M in Ireland. So therefore, I don't know where you got that from. So you obviously took an example from somewhere else or somewhere, and then it was all shared around between a number of people, because there's a good few people that put the same thing down. And that's what I'm concerned about, is that you're just copying from each other and not thinking about what you're doing and so on, because there's blatant mistakes. If someone makes a blatant mistake and I hadn't, there's no way that you could have picked it up from my lecture, then you have to pick it up from somewhere else, and it's unlikely that everyone has just randomly come across this from somewhere on the internet or wherever you have been looking in there. So that's one common mistake. So again, I'm going to come down more heavy on this in terms of if people are just copying from each other, you need to really think about what you're doing. Okay, so that's the partial factors of safety. So that was one mistake. And then the second mistake then, which would have come out from the same kind of thing, was that we require table 3.1 in Eurocode 3, Part 1 to get the material strength. So I gave you S275 steel, so that's the grade of steel in there. And then from this table 3.1 in there, you can see that for a thickness less than 40 millimeters, the yield strength is 275 newtons per millimeter squared, and the ultimate strength is equal to 430 newtons per millimeter squared. So some people had 265 here and 410, and that again comes from a table step. Yeah, hopefully I'm back again. So the thing's spinning around there that it disappeared. I'm on campus, so I don't know why the connection is dropping. Hopefully you can hear me again. Yeah, great, thanks. Okay, so as I was saying, that from table 3.1, grade S275 steel, then Fy is 275, Fu is 430. When we have the thickness of the material less than or equal to 40 millimeters, when it's between 40 and 80, we move over here to a lower grade, lower strength steel. So people had 265 there and 410 there, which that does come from other tables, where in some of the codes it tells you when it's between, I think when it's T is between 16 and 40, or maybe 25 and 40, I can't remember the number exactly, that you use a lower grade CLS 265. But that I didn't mention anything about that in the classes. This is the table I told you to use. So therefore, again, concerned about that. And it was common that those that used the higher material factor safety of 1.1, they also used a different value here for the Fy. So you need to use the documents I asked you to do, download the ISEN 1993 Eurocode 3 and go and look at that yourself, and don't just copy straight from an example on the internet or from somebody else in your class. Okay, so that were the common mistakes. Has anyone any comments or questions to make on that? No, so everyone crystal clear, because it's going to get a bit more complicated now in terms of the design. So you really need to understand that part, because we're going to move on to a little bit more complicated part. So please do ask questions. As I said, if you have a question, if you don't know something, you're not sure about something, then you're damn well sure that there's a whole heap of other people in your class that have similar questions as well. Okay. So if there's no questions, I'm going to move on. Okay, so well, what we have done up to now was a symmetrically loaded section in there. So there's no, so we load it directly through the centroid of the section in there. So where's my ruler? So in the get the ruler, we just caught the end, and we load it straight through the centroid of the section. Okay, or very close to the centroid of the section. So the centroid of the section would be halfway through the thickness of the section. We connected onto both ends and loaded it in there. So it's very, very close to the centroid of the section. However, if we have a section that's, try and draw this. So if we have a section such as, sorry, now I'm going to have to just think how to draw this. Okay, so if I have an angle section, okay, so there's an angle section. Sorry about that. Okay, so it's not too easy to draw with the mouse. Okay, so it's supposed to be 3D of an angle section. Okay, so there's an angle section in there, and if we put the hole for connecting it in here at the bottom, along the bottom, so we're going to put a bolt in there, and then that's going to be connected to, let's say, a plate that's coming out here. Okay, so this is the plate, and that plate is welded onto something else, or it's connected onto something. Say it's another hole there, and there's another angle section connected onto that, so they're connected on together. Okay, so if I look at this, then this centroid section is along up here. Okay, so the centroid section is there, whereas the force that I'm applying is through where the bolt is here. So that's the force that I'm applying. Okay, it's through there. Sorry, a bit of a mess. That's the force. Okay. So we can see that the difference between the centroid up here and the force down here is that distance E. Okay, so that's an eccentricity, and we know that a moment is equal to a force times an eccentricity. Okay, so we know that a moment is equal to a force times an eccentricity. So if we have a force that's pulling out here, we have an eccentricity E, so that's the centroid. So the force is away from the centroid of the section. Therefore, that's going to put some sort of bending moment into the section. So as well as having our axial load, like what we had last time, so in TD, which is the axial load that we're trying to stretch it apart by. So whatever we're trying to stretch it apart by, that we also are going to have a moment at that connection, an induced moment at the connection, because the force at the end of the connection, where we're connecting this member onto some other member, is away from the centroid of the section. So therefore you're going to induce a moment. So moment is force times distance, and in this case our force is nt, our distance is the eccentricity E in there. So we have to design the section for the axial load in the member, like our previous example that we did, plus this moment at the end of it. Now what the code will allow us to do, the code will allow us to analyze this. We have two options really. One option is that we can analyze it in detail, where we take into account, we work out what the bending moment is at the end here, and we work out what the stresses are associated with that bending moment included in the design. So our bending moment being the eccentricity times the force that's applied. So we can do that. However, when it's a lightly loaded member, so if the member is lightly loaded ties, then we can use an approximate method, and we can say, well, we can look at the net area. So the net area being the area, cross-section area through here, minus the hole, or the number of holes that we have through it, like what we did in the previous example. And we can change that net area to an effective net area. So we can use an approximate method. So we can use a beta value to reduce down the net area, which I'll show you in a minute. The justification for being able to use this simplified method is that the eccentricity is reduced away from the connection, and the eccentricity also reduces after ductile yielding. So if we take this example in here, and so when I'm back over here, we'll say in the section, over in this part of the section here, at that stage I have a uniform stress throughout the section. So whatever the stress is here, it's the same stress all the way along. So when I'm looking at my say stress strain graph, okay, and I have like that. So that's the ultimate up here. That's the yield here, so Fy, the ultimate up there. Okay, so when I look at the stress strain graph, the stress, so from this graph, so I'm going to stretch this because I'm pulling it across here. I'm going to stretch it. We said that the strain is equal to the change in length, so how much I stretch it by, divided by the original length of that member, so whatever that length is. So this is the length of the original length of the member. So that strain is equal to the change in length divided by the original length. So however much I stretch it by, when I get away from the connection over here, I'm going to end up stretching all of that by the same amount. Every single fiber all the way through the cross section with the same amount. So I'm going to have the same stress right across it. So this, so the fact that we're loading eccentricity isn't going to affect the stresses back away from the connection over here. However, as I'm close to the connection, so somewhere here close to the connection, I will end up having higher stresses here, let's say, but then they'll start to taper off. So I might have higher stresses there, and then I'll have lower stresses out over here. But as I said, then they start to taper off, and then you get uniform stresses all the way through the end of it. So the justification for using an approximate method is saying that this eccentricity starts to reduce down away from the connection. So if I was able to draw that eccentricity with, so the eccentricity is up here at the start, but then as I move away from the connection, it'll move down into the bottom in there. So we don't have the same moment in there as we move away from it. So back here where we were checking before for the plastic resistance, it's less affected by the eccentricity of the loading. So that's one side. And then the other side is as we yield the section, so as we go past the yield here, so normally around the connection we allow it to go towards the ultimate in there by using 0.9 FU times the net cross-section area. And as we do that, we're into the ductile area, and eccentricity again is reduced as we get into the ductile area in there. So that's the two reasons for justifying for being able to use this approximate method. So what is the approximate method in there? So sorry, if I just see if I can switch over to another. So where does it say that? Try again. So just try and show you that in the code if I can upload the code. Okay, it's just converting here, so I'll try and upload it. So basically in Eurocode 3, part 1, that tells us, that basically highlights this, what we're allowed to do in it, and it tells us to go to Eurocode 3, part 1, to go to this clause here, part 1, part 8, Eurocode 3, part 1, part 8. Okay, hold on, let's see if I can share this now. Okay, so hopefully you can see that. Try and get to the tension member. Okay, that's the cross section that we were using. Okay, so that's the tension member in there. Hopefully you can see that okay. So the tension member, so you can zoom in. If you look at the controls on the left hand side, you can zoom into that. I'll zoom in here on mine, but I don't think it zooms in on yours. So you can, there's controls on the top left that allows you to zoom in and out of the documents that I share there. So in here, so we have clause 6.2.3 in the tension members. As I said, the demand divided by the capacity has to be less than 1. We have the plastic resistance AFY gamma M0. We have to check for that. The design resistance at the net cross-section area at holes for fasteners in URD 0.9 A net FU gamma M2, where gamma M2 is 1.25 in there. And then if you look here at 6.2.3, number 5, it says for angles connected through one leg, see also EN 1993, part 1, part 8, 3.6.3. Now that's actually supposed to be in there. That's a mistake. That should be 3.10.3. So it's a mistake in the code. So for angles going through one thing, see 3.10.3. Similar considerations also given to other types of sections connected through outstands. Okay, so if we have an angle section, that's the eccentrically loaded that we've just shown that example. We go to Eurocode 3, part 1, part 8. So the hardest things about the Eurocode is just trying to navigate yourself around them. So you go into the tension one, you do a couple of checks, then it sends you back up to find out what gamma M1 naught is and gamma M2 is. You have to go to a different place for that. To find out Fy, you have an Fu, you have to go to table 3.1. So it's really just to know where to find the various different parameters that you need. But after that, once you can navigate yourself around, then it's not too difficult. Okay, so if we go then to Eurocode 3, so we said 3.10.3. Okay. So this is Eurocode 3, part 1, part. So this is Eurocode 3, part 1, part 8. So it's design of steel structures, design of the joints, including the Irish National Annex. And if we can get to 313, not too far. Okay, so 3.10.3. This is angles connected by one leg and other unsymmetrically connected members in tension. So the eccentricity in the joints, as C 2.7.1, and the effects of the spacing and the edge distance of the bolts should be taken into account and determine the design resistance for unsymmetric members or symmetric members that are connected unsymmetrically, such as angles connected by one leg. So this is the example that we're doing here. A single angle in tension connected by a single row of bolts in one leg, see figure 3.9. So there's 3.9. So there's an angle section in through the section of it. Here's the elevation of it in there. So if we have a single row of bolts, like either 1 bolt, 2 bolts, or 3 bolts in a row in there, maybe treated as concentrically loaded, so doing the same as what we did previously, over an effective net section for which the design ultimate resistance should be determined as follows. Okay, so I'm just going to zoom in here a bit for myself. So with 1 bolt, the ultimate resistance is equal to 2 times E2 minus 0.5 D naught T FU over gamma M2. Okay, so gamma M2 is the material factor safety, which is 1.25. FU is the ultimate strength, so we go to table 3.1 for that. So if it's S275 steel, that's 430 newtons per millimeter squared. T is the thickness of the angle. D naught is the diameter of the hole, and E2 is the eccentricity in there, which I think we can see it here. Yeah, if we go down to figure 3.9, you can see D naught is the diameter of the hole. E2 is the eccentricity from the top of the section down to the center of the hole, and E1 is from the end of the member into the center of the hole. So in other words, E1 is in the direction of loading, E2 is perpendicular to the direction of loading in there. Okay, so we can so we know those values from the geometry of the section multiplied by 2.0, and that will give us the ultimate resistance of the section at the end in there. So if you think about the last one that we were using the net cross-section area times the ultimate divided by gamma m2 multiplied by 0.9. So that's the difference. Then with two balls, we can use a beta 2 value, A net FU, gamma m2. So if you think about when we have the section that we're designing previously, when we had no eccentricity, then this beta value was effectively 0.9. So we have two balls here. We need to work out what beta 2 is. So we have two balls in this situation here. So we have the distance from the end of the section to the center of the first hole, E1. Then we have the pitch distance, P1, which is the distance between the first hole and the second hole, or the space between the first hole and the second hole. And if we have two balls, then beta 2 is equal to 0.4 if the pitch distance, so the distance between the two balls here, is less than or equal to 2.5 times the hole diameter. Okay. So we work out what the hole diameter is. So let's say the hole diameter is 20. Then if the pitch distance is less than 2.5 times 20, which is 50 millimeters, then we use beta 2 is equal to 0.4. If it's greater than 5, so again, if the hole diameter is 20, greater than 5 times the hole diameter, so that's greater than 100, then we use beta 2 is equal to 0.7. And if it's somewhere between 0.25 and 5, then we interpolate between 0.4 and 0.17. So in other words, if we're halfway between between 2.5 d naught and 5 d naught, so if P1 is halfway between these two, so what's that, 3.75 d naught. So if P1 is 3.75 d naught, then we interpolate between those two, so halfway between those two is 0.55. Okay, so then we put in the value. So let's say, for example, it was less than 2.5 times d naught in there. Oh. So if it was, so sorry, I hadn't got the pointer out there. So just to recap on that. So if the pitch distance, so the pitch distance down here, distance between this hole here and this hole here, so pitch distance P1, if that pitch distance is less than 2.5 times the hole diameter in there, then we use beta 2 is equal to 0.4. So here's the hole diameter. So if the hole diameter is 20 millimeters, then if the pitch is 2.5 times 20 is 50 millimeters. So if that value there is less than 50 millimeters, we use beta 2 is 0.4. If this value here is greater than 5 times the hole diameter, so in the example I'm given here with the hole diameter of 20, if this pitch distance here is greater than 5 times 20, that's greater than 100, we use 0.7. So if that's greater than 100 between those two, then we use 0.7. And if this distance here is somewhere between these two values in there, so between 50 and 100 in my example, then we interpolate between those two. So for example, if it's halfway between those two, 3.75 times d naught, if P1 is 3.75 times d naught, then it would be halfway between those two, 0.55. Okay? And then we put the beta 2 value in there. So let's say in this example, the beta 2 value is less than 2.5 d naught, so then we put P beta 2 is equal to 0.4, so we have 0.4. So you see how that means that this now has gone to 0.4 times A net FU gamma M2, whereas if we had no eccentricity in the loading, it's 0.9 in there. So we can see what the eccentricity does, whereas if the second hole is a lot further away, it's 0.7, so it's still 0.9. So the best you can get by playing around with the hole spacing and so on will be 0.7 times the net cross-section area. So it's never going to be as good as connecting a section would have a no eccentricity in there. And if we have three balls, it's a similar idea. So we use beta 3, which is down in the table here, beta 3 in there, 0.5 to 0.7. So the exact same idea. We look at what the pitch distance is there. We compare the pitch distance to the hole diameter. If the pitch distance is less than 2.5 times the hole diameter, beta 3 is 0.5. If the pitch distance is greater than 5 times the hole diameter, there's the hole diameter, then we use 0.7. And as I said, if it's in between, you interpolate in between. Okay, so that's the beta 2 and beta 3 as it's described here. And the net cross-section area is the net area of the angle. So what's E2? So E2 is down here. So E2 is the distance from the top of the section down into the center of the hole. So it's the distance perpendicular to the loading from the edge of the member to the center of the hole. Whereas E1 is the distance from the end of the member to the center of the hole in the direction of loading. Okay, thank you. Okay, any other questions on that? It's okay. So if someone else has got the cursor moving around there, I know you can write all over these slides and you can move the cursor around. If you can just have the other little icon there to move around, if you can just take it off, please. Okay, so that's the code. So I'll just go back to the example. Okay, so this is the notes that are up on Blackboard. So it's the exact same. On what we just done there, we went to section 3.10.3 in the Eurocode 3, part 1, part 8. So when I have a little superscript up here is 8, that means you need to go to part 1, part 8. If I have a little superscript of 1, it's Eurocode 3, part 1, part 1. Okay, so that's what we looked at. E2 in there, E1, P1, and P1. So E2 being perpendicular to the direction of loading, E1 being the distance from the edge to the first hole in the direction of loading, P1 is the pitch distance, and so on. And they're the equations that are just straight from the code that I just explained. Okay, so if we have a rolled a section angle like what I drew earlier on, where we have the height, so it's an equal angle, so we have the height the same as the width. So if I draw that in there, so we have a section like this, up. Okay, so that's the height. That's the height, and the other one. So it's equal angle, so both legs are the same length, and then the thickness. That's the thickness of the section. Okay, so in this case, A net is equal to the A net actual. So whatever the actual net area is. If you have a rolled section with an unequal angle, so an unequal angle in here. So an unequal angle, if we have something like this. Up. Sorry. Unequal angle, so we have a height, H, and we have a width, so they're both different directions, so height is greater than the width, and then we have the thickness here, and the other side has the same thickness. So look at my poor sketch here, but the other one has the same thickness as well. So same thickness in both directions. Okay, so that's the equal angle in there. So sorry, unequal angle here. So this is this one for down here. So A net is equal to the net cross section area, and then this is a lightly loaded section in there. And then we have A net, and this one is equal to the rolled angle section, where it's an equivalent. You find an equivalent to the with the same height and width in it. If we have a welded angle ties together, so if instead of bolting them together, if we weld them together, then the net section in there is equal to the actual section in there for the unequal angle in this scenario, and in this scenario it's equal to an equivalent section. Okay, but we won't be doing welded in this example. I'll do a bolted one, I think, in the next example. Okay, so just so this is the Eurocode where I went to. So just as a recap, that we need to go to Eurocode 3, part 1, part 8, and that's the clause I just brought up there a second ago. Go into the code, and that's the associated pictures with it. So we're going to do an example now on this. So we're just going to pause for till 10 o'clock. We'll come back again in 8 minutes time, and we're going to do an example. So I'll probably stop the recording now and I'll restart it again when we come back. So I'll just take any questions when we come back, and then I'm going to do an example of a loaded member, asymmetrically loaded member in there, and then we'll move on to the compression then for the third hour. Okay.